So I have kind of an agenda, which is to, I have a secret plan, which is to lock like some people. I'm not sure quite who they are, but like, I don't know, Kathrin and Marcelo and Evan and some other people with more time to hack around in a room together to make up the tool that should have been, right, now that we vaguely know what it should have been. Except that I don't really know what it should have been, and that's why I want to lock them up in a room rather than me. But I know a whole bunch of facts about what it should support, because it has to support all of those things. And well, you know what was great, right? It was really great. You could just write down, you know, what you would want to write down. And it was concise enough that you could actually read it without huge piles of syntactic noise. And it was smart enough to make parsers for the meta languages that you use in the rules of your object language. So you didn't have to spend all of your time inventing, you know, articulating fancy notation to some theorem prover fancy notation system. It just made a generic context-free grammar parser from the totally ridiculously ambiguous context-free grammar that you probably wrote down. And then it had lots of, it was a whole exercise in ad hoc hackery, right? Francesca and I added in all the things that we thought would be useful, and we were doing, you know, some language definitions like, you know, before and after. So we had a pretty good clue of what would be useful, and we added all of those things. Highly recommended as a mode of research for enjoying yourself and making something useful. And we didn't think it would be very useful for writing papers, but it turned out to be great for that too, so went. But there's a lot of sort of lessons to be learnt from the experience, which are, Marcelo, especially ones that you're probably not thinking about right now. So one of them is this, that there are all these squillions and millions of different actual languages that you have to pay attention to all at the same time. And we had mechanisms to support some of these things, but they were terribly ad hoc. And what we should have had, well, let me just say what some of them are, right? So you write down that, right? And you think, oh no, I'm just writing down my abstract syntax because you're a PL theory person. And then you realize that no, you actually are writing down, you want to simultaneously be writing down the concrete syntax that you use in the rules of defining your operational semantics or type system or whatever, and that's different. And then you realize that also you want to be defining the language of concrete terms because you want the parser that you automatically generated to also check those for you in examples that you use. And then you realize that, well, no, actually sometimes you write examples which are a hybrid of the abstract and the concrete languages because you have, you know, a few meta variables mixed in with a concrete term. And then you realize that, well, you have like, you know, an object language and then you have some extra constructs that you added just to write the semantics with. And then you realize that actually you were defining a whole family of languages anyway because you have, you know, RISC-V and then, you know, 15 different RISC-V extensions, or actually far more than that. And, you know, the new module system that you have just designed for Java in 5 different flavors, which you need to be switchable. And then you realize that, oh, shit, we have a fine generic context-free grammar parser, but actually we want to make production tooling for this pesky thing too, and that's just way too slow and doesn't produce error messages decently. So you need to write a menhir parser instead, and so on and so on and so on. Right? So it seems to me that we were insufficiently taking the sort of giving the language of language constructions enough first-class status. And you know, if we were young and naive and it was the 1980s, we would think, oh no, we're just like combining some signatures of some algebras. But then there's all this extra data that you need to actually make the, you know, the actual vectors and parsers and other tools and, you know, binding machinery that you need to actually get anything done, right? Which that 1980s view would have just missed out, and you would never have paid any attention to it. You know, if you were, I don't know, the ADS group or whatever. Do you just want to say the ADS group or the ADJ group? ADJ. Do you want to say the ADJ group?
ADJ, and they were in the 70s rather than 80s.
Yeah. No, I mean, I was a student with Joe Gogan.
Oh,
well after the 70s. But I guess the group didn't exist
The group
anymore.
formed in the 70s.
Yeah.
Peter, there was another project you might know about, Gilles Kahn's.
Yeah, there've been a bunch of people who've tried to do something a bit like this, you know, including us, and all of them have been not good enough.
So, what are the bottlenecks?
Well, one is, I think that one is actually an honest to goodness theoretical bottleneck, which is that we don't really understand that thing at the bottom, or what it should be, and just how much expressiveness you need for this kind of thing. And one is, a big one is a whole big...
That's about grammars. You're talking about modular grammars.
Well, sort of, I mean, grammars, but together with all this extra data that has to kind of come along with them. And one is sort of...
And there's a balance, right? Because the more expressive or permissive your thing is, the less you can ask it to do. Which is also part of the problem, right?
Exactly.
Like I want something where I can do dependent types, but once you have that, there's a bunch of things you cannot do anymore because dependent types are nasty.
Yeah, so OT was, you know, let you write down things like that.
Yeah.
And in some sense, it didn't know anything.
Yeah.
And that was its glory and its tragedy, maybe slightly overstated, right? Because you could write down syntax, and it was pretty good at some of these different ways in which you need to do that. You know, you could tell it, oh no, this is a grammar of single whole contexts for that grammar, and things like that. Or this is a subgrammar for that grammar, and it would, you know, check some stuff and generate some things. So it knew some stuff about that. But it didn't know anything about the form of the judgments that you were defining. Right? It was just more or less arbitrary inductive relations. Yeah? So that was great for things like this, which was our original motivating example, because Francesco and I and other people had been working on this acute language, which everyone has now forgotten except possibly Neil, which was, you know, a random research language for type-safe distributed ML-like programming with an actual definition, because we thought, oh, we'll write an actual definition, and it was really annoying to write, right, without the tool that didn't exist. Yeah? So for things like that, which are basically all just arbitrary inductive relations, this is very nicely expressive. When you get into writing down semantics for machines, which, oh dear, is the thing that we started doing afterwards, immediately afterwards, there's a bunch of stuff that you want to specify in like a functional, you know, a typed functional pure language of some kind with some level of fanciness of type system. And OT didn't really support that. But we made up another tool that did support that, but didn't have any type dependency. And then we started doing instruction semantics, which is full of bit vectors of length n plus m, and yeah. So it's a very annoying question to sort of pick the limit of expressiveness of the meta-language type system. And I don't know how to do it.
And there's also a fair amount of things that you just can't hope to automate. I mean, like for dependent types, it's a bunch of things that are just hard theory that you can't hope a tool like this to automate, at least not now, maybe in 50 years. But so there's also a balance of like what we can hope to automate in a reasonable way, and what is just arrangeable, but we can do by hand because that's what we like, or at least that's what I like.
Yes. So, concretize what you just said. What might you like to automate that you can't quite, or that you definitely can't?
What I think should be automatable in a reasonable, foreseeable future. I think the sort of type systems I don't think I would be able to write them in something like this and get reasonable things out of it, because they're just too nasty type systems.
So, I mean, if you write this in R, all that you would get out of it is, the inductive relation definition in rock plus typesetting. So are you saying that's no fun because you don't also get, at least a checker for complete derivations? Or are you saying you couldn't even get that in a decent form?
So maybe I could get that in a decent form, but I don't think I could get, so I don't mind writing a big inductive type for typing directly in rock. And I don't think it's that useful to write it in something like this, because I don't think the tool can give me a lot of useful things on top of the type system.
Is that the only way that you'll ever get the LaTeX file for your PDF that is actually matching the Coq one?
Okay, maybe that's one thing. But what I mean is that the sort of things that I would be interested in and that look more reasonable to me is maybe some things for untyped terms, but as you said, like all sorts of context and context lemmas and like congruence closures of a bunch of things and reduction relations and like these sort of things on maybe untyped objects would be more feasible or very boring to do and would actually be
what sort of Kathrin's aspiring to,
yeah.
as it were.
Yeah, and I'm using auto subs and I'm happy. I mean, I think it could be doing more, but I'm happy by what it's already doing, and it scales to the sort of crazy things I do in a way that's reasonable.
Yeah, so I want to add a comment that in some ways Auth is already too expressive, because you can write down an arbitrary inductive relation here, and say you're writing down a bidirectional type system, you want the relation to be mode correct.
Yeah.
And if it is mode correct, then you know that you can automatically derive like a functional version of these rules. And so it's a case where shrinking the expressiveness gives you sort of more stuff you can get out. And I think something similar happens with lem, where lem is just slightly too expressive in the amount of recursion it permits, because that lem is mostly functional, or it's entirely purely functional, but you can have like sort of recursion however you like. And this means embedding into Coq or lean gets much harder.
So there's a couple of things there. So lem, well, for this, you might want, retroactively, a design principle of OT was to let people write down a simple thing and then stick on in arbitrary annotations whatever other information was handy. Right? So you might easily say to yourself, I want to write that, and then next week I want to be able to add some mode information. Right? And sort of keep the generic expressiveness, but only for some purposes. So lem is sort of basically the pure fragment of OCaml as a spec language, and we didn't build any kind of termination checker into it. But if you are using it as a front end for a prover, then you have to fight with whichever of those checkers.
So like
you
going
have.
into Hall or Isabel, like I think it works pretty well, because there, you define functions as a set of equations, and then you prove that it's actually defining a function.
Yeah.
But in like Coq and lean, it has this syntactic check.
Yeah. So for Rock, it's annoying because you can't just syntactically postpone that proof until later very easily.
I'm in a hard place because I don't know what rock is.
Coq, rock, dock. Just don't. But then the other thing about them is it doesn't have any kind of computable, non-computable distinction, right? And Dominic Mulligan and we and notionally with Andy, although we never actually really got around to it, were going to think about what we would do instead, and then we got distracted by other actual work. So it's not exactly that it's too expressive; it's that it's not informative. It doesn't let you be informative enough.
So, how hung up are you on syntax?
I'm quite hung up on syntax because people have to define it and auto-generate tools that work with it.
But once you get it into some abstract syntax form, isn't that the real thing?
No, because a lot of the things that you want to do rely on the actual syntax, really working and being able to parse it
No,
and
that's
print
true,
it.
but that's kind of extra logical.
I don't care whether it's extra logical. It's a thing that we need to.
No, it's important in that sense, but it's more important to get the abstract syntax right, because those things you can have industrial things that take care of advice on things like that.
No, but they don't. Right? If you say to yourself, "Aha, I want to write down the semantic rules for my language," right? If you don't have something like what we did here but better, then you can't parse the rules that you want to write even. And if you don't have machinery that makes it really easy to define the syntax that you need, and at the end of the day get a production parser out, then you just can't use it at scale.
So then, what are your requirements on this parser generator that would meet your needs?
So what we did here was Scott Owens wrote a generic, I don't really remember, a generic SG something parser for arbitrary context-free languages. And then, but because you're only writing down these very short terms, and because it's something that Opt does that one scarcely ever normally does, because these things have to be strings of particular forms, you have T ranging over types, not arbitrary strings as variables. So in that sense, this language is quite unlike normal programming languages. Because of those two things, it's normally not ambiguous when you have actual rules. And just occasionally it is, and the user has to say something. But if you try and use that parser to parse, object language terms, it's way too slow. And there's too much ambiguity, and it's no good. Right? So I had like a little idea.
No, but you're interested in the syntax of the meta language. It's the meta language syntax that's the focus here, right? It's not.
Well, no, both. Both. Right, so here, on the left, one has defined the abstract and concrete syntax of some object language, and the tooling generates a generic context-free grammar parser, sort of instantiated to actually that concrete syntax and that, in multiple different flavors, and uses that to parse the rules.
Do you have a sense for how many languages actually use generated parsers as opposed to handwritten ones?
I think basically none, probably, because it's never quite flexible enough, and because all of the real languages have accreted some weirdness.
Go uses a LR parser.
Which?
Go.
Yeah.
I think that's also part of the picture, is that if whatever the tool generates is not epsilon distance of what I would have done by hand, I'd rather spend 3 weeks writing by hand the proofs of all the dumb syntactic lemma, because then it will make my life nicer for the next 2 years I'm doing the semantic.
Yeah.
So there's this, right? If I can avoid these 2 weeks, I'd be very happy, but I'd rather pay these 2 weeks than spend the next 2 years fighting with whatever the tool generated, which is not quite as
Yeah.
good.
So this is totally true. The tool has to be really good to be, to sort of get off the ground. But going back to parsing, so So I later came to think that what we had done here was in some sense stupid, right? Because, I mean, in many senses stupid, but in particular it was stupid in that if you have written like a many parser for your language of choice, for the totally concrete syntax, and you angst it about the concrete syntax in the way that you love to do, and the way that you have to do to make an actual usable programming language, then the abstract syntax that you want is, I kind of hypothesize, always, or almost always, morally a quotient of the grammar that you wrote, that you told many about. Right? And so I hacked around for a few days, a couple of years ago, a few weeks, a couple of years ago, and I sort of taught Opt to do that. So you can give it some concrete syntax grammar and a quotient relation over the, a partial equivalence relation over the non-terminal roots, and it will check that those are not inconsistent with each other, and it will construct the abstract syntax types from the quotient, and that seems to kind of work. Right? And it's
essentially what semantic actions do.
I have no idea.
But what in Minier you put in curly braces after the rules.
Oh, well, no, but it's constructing the types based on a quotient of the grammar rules. And so it's not. But
you would hope that if you have something to construct the types, you would also have something to quotient the terms as well, right? To construct the abstract syntax tree from the concrete syntax tree.
yeah, I think I sort of hear maybe Ott even checked that you said the same things in sort of the places where it should be the same. I can't remember how proper I was about that. But that sort of, I mean, that goes back to Mevan's point, right? That I think to make something which is kind of production usable, one might have to go in this direction of having the concrete thing and abstracting from it rather than expecting to cleverly generate something which is as good as it needs to be.
So, for instance, the first AutoSubst plugin was doing something like that. It was taking basically an inductive definition in Coq with a little bit of slight annotations on top of it, and was doing very fancy LTAC to generate from that inductive definition a bunch of things.
Mm-hmm.
But the first object was the inductive definition to basically rewriting by hand.
Mm-hmm.
So instead of trying to have something from the outside generate that thing the way you would write it. And I guess this approach has advantages and disadvantages. The advantage is that you write the thing that you would actually write in your everyday life, and you generate things from there.
But you write the thing that
it's much less flexible than what you're doing.
You write the thing that you would write in
that
your
I want.
everyday life.
Yeah, that's the other thing.
But not the thing that your language implementer would write in their everyday life.
Yeah.
Yeah.
So this is a bigger question than for us, which is this debate versus generated parsers versus handcrafted ones. Obviously handcrafted ones will, be more efficient. The question is, can you find something that's easy to generate and sufficiently efficient? Is that something that you think that generated parsers will never?
Well, I think generated parsers from a carefully designed many grammar can clearly scale to non-trivial programming languages. But this kind of I have no ambition to be a parsing researcher, right? But it's good that some people are parsing researchers. Whether one could get this kind of context-free grammar thing to work at a bigger scale, I'm sort of a bit skeptical, but I don't really have an opinion. But being able to generate, I think it is very tough to generate a production quality parser, with error reporting and so on, that will be good enough in Mevan's sense for things which are beyond perhaps a large but still toy language invented by one academic and their friends for their own purposes. It's just quite hard to make that kind of generation sufficiently clever.
But was there like a lot of work in Minier specifically on doing good error messages where you attach the error messages to places in the
yeah, there is something which I don't really know.
but I thought they actually use that for the OCaml parser.
Yeah, they do.
Yeah, right. I think the OCaml parser now is one of those languages that uses an auto-generated parser with Minier, and they did decent work on error messages.
I guess when I was being skeptical, I mean, there are different levels of generation. I was thinking of generation sort of from this kind of thing to maybe a minute parser, not the second step there.
I guess the question is also like how wide can the because I mean we're talking at the same time for generating production ready parser and from generating fancy lemmas for me doing theory.
Yeah.
And like I guess part of the question is also can we do all of these things at the same time from the same data, or from like different sorts of annotation on the same data maybe.
I mean, I think that I think is like a non-trivial but noble goal that one should aim at. I mean, I think one should definitely be aiming at that if one was doing anything in this space.
Well, I mean, if you limit production to languages like Agda and Coq, which are production but not like Java,
Yeah.
I think it's entirely doable. Like, the thing is that for serious production languages like Java and whatever C or whatever, even parsing starts to become an overhead. So they do handwrite things in order to make their compiler like 0.5% faster. Because you've got like 100,000 users, it's like a worthwhile trade-off.
Yeah. Maybe that is a fine segue into Gavin. What happens in the world out there?
About parsing.
No, I mean about the whole Java semantics.
So for those of you who don't know me, my name's Gavin Bierman. I used to be a long time ago in the computer lab, working with Andy and Peter and doing stuff on separation logic and categories and whatever. But now for my, something happened along the way. I now work for Oracle and I work on Java. Since there have been meetings about specifications, I thought I'd show you what specifications mean in the real world, so in particular in Java. And I think there was some mention earlier this week about ugly specs. So these are all ugly. Sorry about that. So we even have a section. So if you go to the Java webpage, there's stuff about documentation. And so here we've got a section on specifications. So I'm just going to walk you through some, just to show you what they actually look like in real life. And I'll tell you some stories as I go. So API specifications, so everything about the API is specified. So here we are. Here's some modules. So we go inside a module. There's some packages. And you can click on them. And there's all sorts of stuff, right? So we've got, and there's lots of pros. So it's all pros. There's nothing formal, nothing formalized. And we go right the way down. So you go all the way down to, particular packages, and there's code and stuff like this. So this is the spec that all developers read. Okay. So this is what they're doing all day when they're writing Java code, is that they're looking at this called Java doc, because it's embedded in the source code for the API, so that we have a sort of a sub-language for writing these sorts of specs in Java code, and we have tooling that rips it out and generates this HTML, and you can write that Java doc in Markdown now, and so we've got various supports, and it's got support for snippets and all of this. And this, to a certain extent, is kind of the most important spec, because this is what developers look at. So we have to have examples, we have to have things written in a way that they can understand what's going on. Okay, let's go back. But probably more pertinent to these sorts of meetings are the language and VM specs. So big news in the Java world, which probably hasn't filtered down or filtered up to the lofty heights of ivory towers and so on, is that we now actually have new versions of Java very quickly. So before, Java was kind of feature driven, so they would decide on a big feature like generics, and then try and figure out how to do it, and they would say, oh, maybe in 2 years, 3 years, 4 years, 7 years, and then finally come out with a new version of Java with that big feature. So these features were typically big, and you can just look back and you can see that some, and I think most companies, are extremely bad at guessing how long it will take those things to be released. So I think in kind of the modern era, and certainly in the cloud era, this is deemed to be unsustainable. So since Oracle, like all companies in this space, we're a cloud company, so everything's about cloud, everyone wants, and people who live in the cloud, developers who live in the cloud, want the latest thing all the time. So they expect things very rapidly turned over. So about 5 years ago, 4 or 5 years ago, we switched to being a sort of calendar-led release cycle. So we have 2 releases a year. And we add new stuff into that release if it's ready. And if it's not ready, you wait for the next 6-monthly release. We also introduced a new idea at the same time, which was what we call a preview feature. So this is basically testing out things, but not like alpha or beta versions. So these are things that we think are kind of ready, but we want people to give us feedback. Because the reality is, you know, Java is, whatever it is, 20-something years old. So it is a dinosaur, right? And it's not going to go away. So it'll still be there in another 20 years. There's a lot of Java code out there. There are a lot of Java developers. So you saw in the graph that Peter showed. I don't know what the axis is, but I think one I read recently is like people whose everyday job is writing Java is like about 15 million people. So that's 15 million people every day writing Java. So, you know, it's kind of a serious business. And what that means is that if you mess up for all time. And I'm not going to comment on whether there are mess ups, but there are definitely things that I wouldn't have done. And I'm very conscious that a future version of me here in 20 years will be talking about things I've done that were terrible. But so we have these sort of preview features. So we try things out, we get feedback, we have expert groups, and we have, you know, anyone can send feedback. And then we maybe try another version. So typically we preview things for at least 2 cycles, so at least a year. But some are cycling for 2 years while we're making changes, or we're not convinced that enough people have tried it, or we're trying a very big experiment internally with it, and we want to see how it goes. So we produce big ugly specs. So I think this, which one was that? So here's the language spec. Here's the current one. So there I am, and it is very big. It is about 859 pages, I think. Yeah, 859 pages. So that's the scale of spec you're talking about. And it's quite complicated. Let me just, let's get the HTML version. So let's just pick something at random to have a look. So, you know, we've got complicated notions between, so this is talking about type conversions. So this is something you would typically, you know, write with a two-place relation, but we've got all sorts of weird stuff, and there's all sorts of weird ad hocery. We've been looking at this a lot at the moment because we want to kind of streamline it. And this is not a beautiful relation between 2 types. This is just an ad hoc set of stuff that somebody thought of in the 90s and hacked up, and which causes us all sorts of problems. So let's take something else. Let's take some expression or something. I know. So I should say the first spec was written by Guy Steele, and we're all still indebted to Guy. He's the king of writing specs, and a lot of this spec is really very beautiful because deep down, if you look at it, you can see that Guy's a formalist. So he writes things very precisely, but we basically don't want to write maths because no one will understand it. The gap between this room and those 15 million people using Java is quite big. So nobody will get it if it's kind of really formalized. But you know, Guy here is talking about...
but on the other hand, I mean, the English language that's there is pretty
yes,
restricted, right?
it is. So we have a huge struggle of trying to write English that's precise enough to actually capture what we want and still be readable by our readership, which is also quite varied.
So, I mean, the gap is maybe not as,
Yeah. So what else did I want to say? Right, so let me show you, I'm going to show you another bit of the spec. So this is the bit of the spec that everybody complains about, which is this one. So this is chapter 16. So Java has this idea that it doesn't want you to use a variable unless it's certain that you've initialized it with a value. Okay, seems very sensible. So it has a notion of definitely assigned. And so Guy set out a load of rules. So he says, oh, this is readable.
make it a little bit bigger.
A bit bigger. For some reason that won't.
Twice as bigger.
There we go.
Good.
Better?
Yeah.
So Guy basically at this point starts setting up some relations. So he's now saying there's a notion of whether a variable is definitely assigned before something, definitely assigned after, and then we've got Boolean ones, so when true, when false, and then he sets up a load of rules. So let's just pick some at random. And this is basically following the kind of semantics of, so this is like an abstract interpretation, right? He's really actually setting this up. So it's assigned after you've done a conditional, so A or if A, then B or C. When true, so that thing will return true. When, well, now we just need to look at the cases about B and C, right? And he really goes through the entire language and sets out all of these rules. So in fact, I wrote these ones. But, and this is the section that every developer complains about. They don't get it, right? Even though this is the one that's closest to a logical relation, as you can imagine, because it's literally that written in English. It's the one that all developers complain about, that they don't understand what it's doing. Whenever we get new testers in, it's always the one that I get all the emails from the new testers. They always say, I don't get what you did here. It's always this section. This is like the really hardest one to grok for people, and yet is the closest one to the sort of formalization, which is interesting.
But which direction does the cause and consequence go? Is this one written in that style precisely because it's the hardest one, or is it the hardest one because it's written in that style?
I don't know. I mean, I can imagine writing it another way. I think this is a beautiful way to write it because this is actually how I think about it. And I should say, I mean, there's an oddity at the moment, right, in the Java team. So if you look at the people designing Java, so it's me, so I have a PhD in theory. Dan has a PhD in programming language theory from Rice. There is Alex, who has a PhD in programming language theory with Sofia Drossopoulou. Our main compiler architect has a PhD in programming language theory with Marco Veroli in Italy. So, in fact, everybody on the team has a PhD. So we're kind of, behind the scenes, when we talk about these things, all the emails are with gammas and 10 stars and stuff. But then we turn it into English for everyone else. So it's kind of weird.
Are there cases where you discovered that the English was ambiguous and you had to disambiguate it?
Yeah.
I'm thinking in terms of, you know, there are long sentences there where you can get lost about the if
Yeah,
you
we-
parentheses, then it would be a lot easier
Yeah.
to see what.
No, we tweak, everything gets tweaked all the time. So I have a whole pile of, I mean, you can go to the bug database, it's public, and you can see all the specs, bugs that people have thrown in where they don't understand something, and so we tighten up the language to make it a bit clearer. And of course, there are real bugs as well. Yeah.
I mean, this looks like, something that you would want. This looks like a really good documentation of the rules. So it's hard to write a spec that caters to all the stakeholders.
Yeah.
So who is complaining about it? Is it programmers who don't understand what they need to program? Is it compiler writers?
So it's a very good question. So we have different readers, right? So at the very top level, so we're in business, right? So everything's driven by lawyers. So if you look at all the licensing around Java, whenever you sign a license agreement or whatever, if you kind of zoom in on all the contracts when they talk about Java, they actually end up defining that as the specification. So the slightly terrifying bit of this is this spec is kind of underpinning all the legal framework around all of our contracts with everybody around Java, which is mildly terrifying because it's literally my Emacs buffer and me doing stuff and this whole sort of tower coming down to that. So that's one set of readers, which actually people are arguing. Probably the primary readership are other compiler writers. So there are other companies who build Java compilers. So we know them all. They get special responses from their emails and so on. But we're trying to spec it so they understand what a feature is so they can implement it in their compiler. And obviously we don't leave it to the last minute, so everything's done publicly with them so they can see us, what we're doing as we're developing. So that's one set of reading, and obviously that's super important because we do get sometimes people saying, hey, we can't implement that for reasons. And then we have to figure out if there's anything we can do or nothing we can do or whatever. And sometimes they say we don't get it, we don't understand or whatever. So that's one set. And then there's the developer world. I don't think any of them ever read the spec. I don't think anyone's ever read it top down. So they tend to skim through if they don't understand. They tend to read more the informal documentation that we write about describing features with lots of examples. They tend to be driven down there, but then they go down. We have a whole test team. We're obviously testing the whole, our compiler and everything. Their work is very heavily tied to the spec. So when you get a license to implement Java, you get access to a compatibility kit. And that compatibility kit is actually, whatever it is, 100,000 tests with expected answers, and you can just run that test suite over your implementation. That test suite is absolutely linked to the spec, down to the line. So when the test engineers are writing tests, they literally read a line from here, and they write tests, and internally the test has a back pointer to the sentences. So they're so we have an internal requirement or usership of the spec.
That would seem like the kind of the gold standard that you don't need to understand the spec, just pass the tests.
Yeah. So that's the service that we provide, right? So if you get that compatibility suite, that's kind of the most complete testing of the specs that we know of, that we generate. Yeah, sorry, Neil,
Yeah, I was just going to ask about the definite assignment rules, which are actually something I've looked at. So
Yeah.
they look like a flow analysis to me.
Yes, they are. Yeah.
And so was it the other compiler writers complaining about them, or was it the testers who were complaining about them?
The testers complain about it.
Okay.
Because they're trying to, because they write their tests against the spec.
Okay,
Right?
so
they want to read the English and write another test, and they don't get the rules. So then, or if I write some new ones because we've got a new feature coming in, then they get. So I want to just.
Is there any interest at all in? I mean, it seems that this spec is, it's not that far from something in which you could maintain, as it were, that the real spec is a piece of prologue or something, and
Yeah.
you generate a natural
So
language.
hold that thought, we'll get to it. So I just want to show two other bits of spec, then I'll stop. So one other bit, this is another bit so that we have a bit of type inference in Java, so you invoke a generic method, but you don't pass the types, and we try and work out what the types would be based on the arguments. And this is another odd part of the spec because, I mean, you'll like it in a way because it's the bit of the spec where
It's got symbols.
it's got some symbols. In fact, the symbols are even Greek. Look at that. So we have Greek symbols. So this is actually a constraint solving. We recast the type inference problem as constraint solving. So we show you how we generate constraints, then we show you how we stir them up and try and simplify them, and then we show you how to solve, to get a solution from a set of constraints. So this is like a complete outlier in the spec. It's kind of like there's nothing else in the spec specified like this. But this is actually how it was designed. So I didn't write this, my colleague did. And this was kind of how it was designed and figured out. This was actually bits of this was a PhD thesis, and I think an Uppsala paper, I think. But then he got hired and put into the compiler. One other thing, yes, so Prolog, thanks for that, Andy. Let's just pivot and look at the VM spec. So the fundamental, if you want to prove a property about the JVM's safety guarantee is that we never confuse objects with primitives. That's it, right? That's actually the type distinction that we absolutely guarantee. So how do we do that? Well, we do it because there's a process known as verification. So we load in a class, which is the result of compiling Java. So you take Java, you compile it, you get Java bytecode, and then the VM reads the bytecode and then executes it. But before it executes it, it checks it. And this checking is known as verification. And if you actually look here, it says, oh, the way we think about verification is actually by type checking. And we will actually tell you precisely what's going on in Prolog. And so, you could convert these to symbols if you wanted to, but every single, so let me just go through to some examples. We do actually, so here's the type that we're going to generate. So we want to check, now this is kind of, I don't know, how you would do things in the late 90s, early 2000s. I don't think you would do it like this now, but it's sort of saying, well, obviously things have types, but obviously we want to track some other properties, like is it an uninitialized thing? So they just smudged this all into one big type system. I think nowadays you would use slightly more sophisticated type theory to do that, but it's okay. And then they literally go through, so these are some auxiliary ones, they literally go through, various things talking about how verification works and how it operates over the stacks and so on. So this is about as close to a mathematical spec as I think we have. I think it's super interesting and perhaps a little bit underappreciated that we have actually got that's an executable spec. It's actually in the repo, that code. It's actually run. So
the testers use that as an oracle?
As one of the oracles, yes. I wouldn't like to say on the record exactly how much that's used, but it is in the Prolog code is in there, a Prolog engine is in the test environment. There are tests on it, but obviously most of the tests are on the actual reference implementation. So, but it's a real executable spec, so it's kind of neat and I think slightly underappreciated. And in terms of kind of the meeting earlier this week, this is kind of the interesting thing is this is the absolute heart of the claims that Java's a sort of safe programming environment is actually because we do verification and we believe there are no there's no flaw in that process, although I don't think the entire system has been proved correct by anybody. But it's probably the most tested thing, because obviously every single Java user is firing things on the JVM, and there are many, many billions of JVMs out there, both on this planet and on other lunar objects and all sorts. Seems to be pretty good, but yeah, anyway, so I think that's, well, there you go, that's life in the trenches of real specification, so maybe I'll just stop there.
That was great. I think I would quite like to continue with that for the next 2 hours, but maybe I will just ask you the $30 million question, which is, the constraint on readability is a big one.
Yep.
But for your internal purposes and for giving an oracle for the rest of the language spec that the testers could use, what would be sort of the blocker in making a mechanized version of the other 870 pages?
It's a good question. I think, well, there are just boring things along the lines that we heard earlier this week, which is about how companies view risk and where they want their risk and their costs to go. And costs at the front of a project are generally not received very well by management, right? So, and there is, perhaps won't be shocked to hear, but there's somehow, we're in an industry that's completely willing to accept, a 10-year tail of technical debt because we didn't do the right stuff first, and maybe we'll have 10 years of tidying it up afterwards, but that's kind of accepted, so which is a bit depressing. I don't know about Oracle, but when I worked for another big software corporation before Oracle, we did a project. I did a project with Simon Hayden-Jones where we was contacted by a team in the database group who were building something that was enormously complicated and was coming out, and they were worried that they didn't really understand. They used to have these amazing meetings that we sat on where somebody would say, what do we think this query will do? And they would all argue because they hadn't actually finished implementing it yet. So it was like really weird. And so we wrote an executable spec in Haskell. And they liked it because we could actually answer the questions in their meetings because we could type it in and run it. But when it came to us saying, here it is, would you like it? Why don't you check it in to the repo? We were absolutely blocked. And the blocker was that they did not want to take a dependency on Haskell or any other tools that they didn't know. And they didn't, at that time, want to own Haskell, and I suspect that's still true. But that's a real, so I'm not saying that's the case in Oracle per se, but that's a real concern that I've heard from other people in industry, which is just, say let's say we decided we want to spec it, we don't want to take dependency on code that we don't know is going to live for the length of time that we've got.
We see the same for RISC-V instruction set stuff in SAIL.
Yeah.
It's not so much that they're scared about SAIL, but they're scared about OCaml.
Yeah. Yeah, so it's one of those things. And I have some ideas about how to perhaps get around that, but it's tricky. So
Putting it to rest.
yeah, so I mean, well, I remember talking to a colleague at Microsoft who was working on JavaScript, and he'd shifted from C# to JavaScript, and he said, why did I do that? Because it's now JavaScript's ahead of C# in the boot sequence of Windows, right? So, I mean, there's a sort of brutal economic model that goes on. And just taking dependencies on things is something that software managers hate doing. Yeah.
So, rather high level, sort of, almost philosophical question.
Yeah.
So So is this that you're showing us, is it, I mean, there's a difference between a specification and a definition, right? One contains the other, I guess. And is this truly a specification in the sense that it's a collection of statements that you like to be true, but some of those statements is not clear how you could make them be true, so that's not a definition, right? A definition tells you, basically, define something definitely, right? Whereas a specification is a collection of things that your assertions about the language that you assert should be true. And I mean, and following on from that, I mean, is it clear that the specification is logically consistent? I mean, you might be asking things that actually can't be satisfied.
Yeah. No, I can't give you any guarantee of that.
Yeah.
And I mean, there are some statements.
I mean, it may say, you know, A should happen, where it's not at all clear, as it were, how you could ever make A happen.
Yes, there are some bits in the spec, in particular around generics. There's some great Giladisms where he just says, let this thing be so. And that's like 10,000 lines of code, and we think it's the same thing, but we don't know. So no, I cannot hand on heart tell you there's a logical consistency.
I mean, in a way, it would be quite good to, as it were, flag within the text when we're doing one thing versus the other.
Yeah, so, I mean, what we are doing is kind of, we know where those things are, and we'd love to actually ferret them out and replace them with something else. I mean, we have other stuff, I mean, just slightly obliquely to your question. So I got a bug report 2 weeks ago from somebody saying, somebody has generated a test, some random person has submitted a bug report, and the bug report comes from a tool that auto-generates Java, and this one has generated a piece of code with an annotation with a constant, which is an array, and the array has 67,000 elements, or 65,500 and whatever it is, and the compiler doesn't work. And indeed, the compiler doesn't work. So what I was arguing with the VM team because there was a genuine bug. It should have tracked it and said no, but it actually set up an array of the maximum size and then pushed the values and then cycled around. And anyway, it doesn't do that anymore. But then I got a bug report from the VM team pushed to me to say, your spec says it works, just says an array, but it only works for an array of that size. So I then had to, after chatting with Alex Buckley, who's very good at these sorts of pompous statements, so we had to write a pompous statement like, the spec tells the truth about the language. You're talking about the compiler.
Yeah.
So, but this is true, right? So if you look, like we say, you know, a generic type is a thing, a name, angle brackets, type arguments. That's it. Or let's say parameter list, right? Parameter list, thing with round brackets, list of things. But in lots of cases, you read the VM spec, it says, I represent those as this C data type, and there's an index which is represented by a, you know, so many bits thing. Well, that immediately bounds it, but the spec says it's unbounded, but it doesn't give you a maximum size. So do we put that in the language spec or do we not? So we don't do that in the language spec. The VM spec tells you what the constraints are, and you have to kind of keep both of them carefully, you know, side by side. Yeah.
Maybe
okay.
We should continue that conversation for another long time. But maybe we should move to one of our other snippets. Well, Kathrin, explain the state
Didn't
of the world.
prepare a speech like this, but I can very
But
quickly
it could be,
say it.
and maybe it could be a shorter thing than Gavin's bit, otherwise we'll totally run out of time and not get any lunch.
That's fine, and I think I will manage with this. So mainly what I worked on was kind of like a very specific syntax for which then very specific proofs were done. So I think, like Mervyn already mentioned, there's the auto-substitute tool, which I mainly worked on. In some sense, yeah, well, it basically generates substitution, and then a certain set of substitution numbers for it based on sigma calculus. There are some theories, like there's some theory of like equational theory behind, so it's like very specific. It's by far not as extensive, for example, as the auto syntax. But then, like for this specific subset, it basically generates substitutions. I think this, like Mervyn already mentioned, like for AutoSubs2, the syntax was changed to be a little bit more on the abstract syntax tree side of things. So to mention on, like to comment on this one, I think there are definitely like pros and cons on having this one. Like I think like something like, for example, like the auto representation is very nice in that it's like very, like much closer maybe to what you would see in a certain rules, but we kind of needed it to basically like make precise on like what we generate afterwards, in particular if we are talking, for example, about mutually inductive syntax and how the variables behave in each one, and then to basically like generate the right substitution and the right substitution numbers, and to still get the guarantees which maybe the user might not even like think about before, like which are needed, and this was the machinery, like why this was basically needed to extend. Another thing worked on, which is also working on quite a restricted kind of syntax, was giving support for basically a coq a la carte kind of like extension for modularity, which also extends to proofs. And
I at least don't know what that means.
Okay, so like basically like the coq a la carte paper, you're probably, okay. So there was a paper for Haskell with coq a la carte, basically like how to put in an algebra way like together like different data types and different like functions to basically not necessarily like repeat code again and again. If this is like, for example, like we were like write a recursive function on it. One extension we did was basically to have a similar version which also works in the proof assistant, to basically like put together certain like data types and then basically like basically carry over like proofs, for example, for type safety or strong normalization. Basically compose those so that like the code doesn't have to basically like be duplicated, which I think goes a little bit in the direction of like reducing basically like repetitive code. I should say that this is like as it's now like very restricted. For example, it assumes that the same kind of like, for example, like variables are used and like contexts are not extended, but I think there are some ways that like some methods out there to basically like extend it.
What's your say this very generically? What's your view of the future?
I think it can be very hard to like extend all the features, like in particular so specific ones. Like for example, like if I'm just thinking of the modularity aspect, right? So I wouldn't like be able to carry all the proofs because like it doesn't hold for all kinds of syntax, right? Obviously, but I think there should be a way to basically like specify like for which parts or like which subsets of the syntax maybe I would want certain features to hold. Maybe like also because we talked before about like very general things, and I think like maybe the hope shouldn't be like to specify like for every syntax to specify everything, but maybe it would be already good to have like a sub part of it for certain parts, and maybe then the other ones are just like supported for certain features.
And on the binding side, is sort of AutoSubs2 as it is like flexible enough and effective enough for some nicely large domain of targets, or do you have the ambition to make it different, or are you sick of it because you've worked on it for a while now?
Well, I have no PhD student working on it, so I should rather not get completely sick of it. But I think there is way more support than there is right now, right? So I think Mervyn already mentioned that he would wish for some additional support from time to time, right? And I think there are some things which, like for example, as of now, AutoSubs supports basically like rewriting. And if you have like two terms with substitutions and like basically like no assumptions, it basically like basically comes down to a normal form and then basically like has some guarantee that it will basically like give you a guarantee like on what like that it can actually prove the lemma if it is true. But for example, like we don't have any like tactics or whatever for basically like matching. Or basically, like if you have an assumption and a goal which has some substitutions in it, I think there is some work around nominal syntax a little bit in this direction and like some guarantees on this. But like for example, something like this doesn't exist. This would be an extension, and also of course, which people here in the room some also know about, like stuff like extensions for syntax traversals, which has been there's been a lot of work around the Strathclyde group, around Ale and others. And maybe also like support, like more support, for example, like inductive predicates, which basically like contain substitutions.
One thing I can say as a user is that somehow there's two aspects to this story. There's the aspect of generating a bunch of lemmas or definitions and so on, which Autosubs does well on the fragment where it tries to do it. And then there's the second aspect, which is the sort of infrastructure you need to make all of these definitions and lemmas usable. Things like notations, tactics, automation, all these sort of things. And this is, I mean, there's like, I think 4 different versions of Autosubs now, but at least on the ones I'm using, that's where the thing gets really frustrating and annoying, and makes the whole first half kind of less usable, because like the automation is kind of set up in weird ways, or there are certain things that I would like to be able to do easily and are not really easy to do. So at least on the proof assistance side, that's one aspect of things that I think is important, is once you've done all of this generation of a lot of fancy lemmas and whatnot, making sure that they can be used in a natural and easy way. And that's also part of the whole like making it good enough story. And I think the hard part about this one is that it's harder to give to students. Because it's easy to give to a student like this are all the lemmas it should automatically prove, because there's a clear objective, but you should make these lemmas usable requires a lot more understanding of like how people do these proofs, how people like set up automation in general and so on, which maybe we've been less good at explaining. Yeah. But I think it's also very necessary if we want to make these sort of tools usable.
Even without the lemmas, in art we imagine something about what the nice shapes of some of these inductive relation definitions would be when you have nested data types, lists of different lengths, and we had some idea in our head about what would be the most useful form, and we were wrong. Well, never had time to go back. Other ponderings on binding and names from anybody?
Yes, I was going to ask about the nominal matching thing that I had problems with.
Louder, please.
Nominal matching approach.
So Autosubs uses the Brown syntax. Sorry? Autosubs uses the Brown syntax.
How do you do the substitution with the Brown syntax?
So first renaming, and then substitutions. So it's basically like a 2-level approach. And then, like I said, there is like basically like a completeness theory, which states basically like if you just like have basically like no assumptions, then you can basically and you can basically do it by rewriting a certain set of numbers which are inspired by the sigma calculus.
Andy?
Yes.
Does nominal Isabel still exist?
Yes, as far as I understand it, it's just about sort of reaching a rejuvenation point in the hands of Andre Popescu and what's the other chap called? His long-time collaborator.
Is it Dimitri Traitor?
Yes, exactly. It's Traitor. So, so they're producing, or have produced, or in the middle of producing something which is wildly more general than it's kind of rejuvenating the data type package in Isabelle, as well as adding all sorts of features to it. So that's all I know. I mean, I don't use it, so.
Does anybody?
Also, I mean, the world of higher order logic is somewhat different from the one that probably most people in this room inhabit, which is some form of dependent types.
So the extensions are that I think they based on this on Andrew's paper on like functorial
Yes.
things. So basically like it's wider category of binders to support. I think also for co-inductive data types. They are the most two.
I mean, the one thing that we should all aspire to that you can learn from them is that how marvellous it is to have features, say in Colk or Isabelle, or in Angler or Lean or whatever, which are making your ability to have richer and more interesting type classes around. I mean, without tying yourself down to some specific representation. I can only do a certain kind of second order abstract syntax grammar or something like that. I provide a way of making data type declarations more exciting. So I can do a data type deriving I don't know what that it represents some between numbers. So that's the kind of thing they have more of than I've seen in dependent types.
But if, God help us, if we were, which we're not, going to make, opt n+1, at least for Coq, is it clear that basically one should be building auto-subs 2 into it? Or is that insufficiently expressive to make it convincing? Auto-subs 2 plus this usability stuff that Mevan was talking
I
about.
think it's a reasonable place to start. Like I haven't tried. Might be an interesting thing to try whether autosubs, one of the autosubs 2 works with the metacoq syntax, and I think it would.
I think it would. Because we discussed it at some point.
Yeah, I think it would. It's rich enough, and I think that's kind of quite a good test case of how.
And that has like dependent patterns and things.
Yes, but basically the main thing it has is a bunch of lists all over the place, and all sorts of kind of nested things.
This
Which well, so nested with lists for sure.
Mm-hmm.
You have a bunch of things where you have like kind of custom data types depending on the data type of term that we nest with, which are more complicated than lists, but it's probably most of the machinery is probably there. You might have to prove by hand that the thing you define as a functor by hand.
Yes, so this is what
But-
is at the moment
Yeah.
done so that you can add
Yeah,
like
But
arbitrary
I think
functors
this
to
should be
it.
doable, and so it's a nice experiment. But I think if it's not there, it's reasonable to like close the gap, and I think it's a reasonable test case of how dirty things can become.
Yeah, well, I mean, one of the things that we learned early on was how crazy the world of bindings for languages which other people have invented are. So yeah, in order to be generically a bit usable, one does have to hit.
So to be fair, metacoq is a very core language, which means, for instance, that pattern matching is not as gory as it gets, because it's like flat, like depth 1, you have exactly one case per constructor, which binds just the right number of variables, and that's it. And like the crazy thing gets sugar to that before we actually try to do the theory. So it's not maybe as gory as it can get in terms of pattern matching, for instance. But still, it's already a good test case of what real life looks like. At least it has lists all over the place. So.
I'm conscious that if we arrive too late at Churchill, then we get no lunch because we have to fight with all the undergraduates at once. And they run out of food. But now it is only past. Let's see, so Marcelo. So at the beginning I had a long rant before you got here about the complexity of the set of all the different abstract and concrete languages that one has to define all at the same time for nasty languages that people actually use. And the sort of the lack in the odd thing that we built years ago of making that sort of first class notion of having all those different definitions be constructible by language constructing expressions. And this is a vague question, but does that have anything to do with what you've been up to? And in any case, maybe for like no more than 5 minutes, you could summarize what you've been up to.
Yes, so I mean, what I do is a bit of a hobby for me, so it's applying the math. So not taking it to the extreme, but I think it could be taken to the extreme in the practical applications, but it's just that I have not done it. To me, what we have, the system that we have in place with DIMA is essentially you can specify any simple type theory. And I can give a precise definition of that if it's necessary, but intuitively there are things like simply type lambda calculus, computational lambda calculus, anything that has a binding operation for variables like primitive recursive functions, first order logic, and so on and so forth. The specification is given by essentially a grammar that assigns to every operator a type that includes the information of binding. Once you have this, you automatically generate the signature in AGDA of the abstract syntax. And now, the way I view this is that one should not only generate that, but should generate that with extra information. And the extra information is, in the simplified case, is a second order structure, which you see as meta variables that may be parameterized by terms. So your object language is first order, but the one you want to implement and work with to talk about the object language is second order. So for instance, the thing that you had in your slide, say, you have x in the context and then you entail t, then you have lambda x dot t. This, to me, does not make any sense whatsoever. I know we understand what intuitively means, but it's not formal enough to be manipulated by a computer. So you introduce these meta variables that are formal syntax to be able to talk about the meta language or meta theoretic properties of the language. So what we have done is, so you specify the signature, and it automatically generates all the AGDA code for implementing the abstract syntax as the inductive data type, implementing the notion of substitution for this. So it's not only capture avoiding, but now the real kind of substitution that you need has to be a substitution for these parameterized meta variables. Because this is how you generate from exactly one equation or reduction rule the set of all instances that you want to compute with. And so we automatically generate, and these two are mutually recursive. So the meta substitution uses the capture avoiding substitution. So they have to build. Now, to build this is non-trivial actually, but, and then, okay, the math is something else. I'm going to save it later on.
But the point is that, okay, you input the grammar, and out of this you output all this stuff, which proves that all the operations are correct. That's the main thing we have done. You can generate in this way equational theories. If you want them, you want to generate rewriting theorems. We have not used it, but it could also be used, I'm pretty sure, to specify operational semantics in the form not of a small step or big step, but in the form of evaluation context, a la Felizen. So this is also a possibility. Then with Gregor, who's there, he was an MPhil student last year, we used this, we attempted to prove a general meta-theorem about confluence. And okay, there is some block of Agda that does not allow you to do the mathematical proof. Also, there was no time to sort it out, but this we will have at some point. So that's one direction in which one can do meta theory. So any kind of simple type theory that's with reduction rules of such and such a state that satisfy some conditions will be confluent. So that's one direction. Then there are millions of other directions one can go for. One can extend this with polymorphism. I've done the math already. I know how it should be implemented, but okay, one needs people to do this stuff. One can extend, do this with binders that are linear and mixed bindings, so some may be linear, some may be Cartesian, so substructural logics, that's also possible to be done. So there are sort of things that could be done. One thing that I found in this, yes, two things is that the first time when I started to do this, quite a bit ago, I thought you just implement the math in the system. And I quickly found out that this is not possible if you want to compute. You see, so you can be very super parameterized on abstractly define what is a data type that supports binding and this and that. But at the time of when you want to compute with it, you have to take decision on concrete implementation. Because if you decide to implement the data type as the colimit of the omega chain generated by the functor, then you will not be able to compute with it. So, and then the thing that kind of struck to me is that to be able to tell the computer how to do the thing and be able to compute with it, I have to change the mathematics and develop some new one, which is, of course, tightly connected with the original one, but not as clean. But all this can be done in all this realm that I'm talking about. It's just that, well, one needs people, but also a reason to do it.
Can you, as a prospect of souping this up to cope with fully dependent things, where everything gets defined in
Yeah, so
horrible bundle?
That I would like to do that. I have a vision of how to do it, but yeah, I need the time really to see if this vision can be done. But that's the target. The eventual target is there. It's just that you can grow in many different directions.
I guess for dependent types, at the moment you could take your thing and just like don't add the types in. You could just do the untyped term representation and still get like all the substitution stuff and whatnot, and then build the typing as judgments outside. It would be less satisfying than having kind of the whole intrinsically typed objects and whatnot. But it would still be useful even for dependent types.
Yes.
Which is anyway, like it's kind of an open research question, how to just do these things in a workable way. So at least the external view, you would still benefit from this sort of machinery.
This could be done now. Is in the old style of instead of writing down your data type that precisely captures the abstract after equivalent, you do it in 2 steps.
Yeah.
And this is there, could be done now.
So just one.
Editorial comment. So there's a whole graveyard of these things that people have read in the past. The art of abstraction engineering is not in achieving the greatest abstraction or generality. It's in finding the sweet spot.
Also, it seems to me that I mean, like you take like AutoSubs. So am I right? In that it's an external program written in OCaml or Haskell, yeah.
Well, there's 3
Which generates some stuff.
Yeah, but like,
Yeah. So I mean, if you're very tied to a particular system, say you're a rabid cock user or whatever, then I think one looks with a certain longing towards Lean, right? Where I believe that they really have done quite a good job at the metaprogramming aspect of things, because you would really write that tool, and the tool that you write is never going to be the tool that somebody else wants, right? So it's better to get fantastic metaprogramming features so that they can write their own tool.
No.
No, why not?
No, because
People are never satisfied with the thing that you provide them with. Right?
well, so they might need to tinker with it, but they want to do their own thing, which is specify WASM or something like that. They don't want to spend their lives becoming a Lean expert. I mean, some of them do, but if you're not aspiring to make something that's actually sort of useful out of the box, then it's a different game.
Also, if it's a very, very big thing, at that point.
Yeah, but the activity of embedded DSLs is going to be an active one.
Yeah.
Anyway.
The other advantage of tying your whatever tooling more closely to the actual proof assistant is that it makes it in certain ways easier. Like it's a very different way of interacting with the thing. Right? The external implementation of AutoSub that are in Haskell, or so Haskell really basically generates strings, right? But you don't have any way to interact with Coq. Then there's an OCaml one which also already starts to talk a bit more with the internals or the APIs of Coq. And there was even an attempt to do something like this in using MetaCoq, but the meta-programming aspect of MetaCoq, so kind of really in that direction. And as you go, you get access to more and more kind of API and support of the internals of the language to like do a bunch of things. The good thing about the OCaml AutoSubs implementation is that now it's in the Coq ecosystem where the Coq devs are responsible for fixing it when they change the internals of Coq, which was a real problem for a while because we were tied to Coq 8.13 to generate our syntax, because that's the version where the thing was written for, and then I and Yannick spent a few very nasty days porting that to the latest version of Coq, but now it's in the place where the Coq people are taking care of the updating, which means that the thing will hopefully survive much longer than if we were doing the maintenance. So that's also part of the question: is the tighter you are to one particular framework, well, maybe you pay that by being tied to a particular framework, but then also you can reap the fruits of being in that ecosystem, and that brings also certain benefits. So
I totally envy the state of having the Coq devs maintain
yes,
things
it's
when they change
amazing.
stuff.
And it's also not on package, so it's really easy to have in your Mac files and everything.
It's easier than the alternative.
It's no, but like, I mean...
Anyone who says OPAM and easy in the same sentence.
Well, I mean, okay, if you already know how to install Coq, it's epsilon more difficult to install AutoSubs OCaml.
Only epsilon 0.
So for
I think the difficulty is even knowing that you have to do it, right?
But for
I
Ott,
mean, other than finding out.
for Ott and Lem and Sewell, we went the other way. We very carefully didn't lock ourselves into one prover, and you pay a substantial cost for that in some cases. And for Lem, the cost was that the generated cock definitions were rubbish. But in each case, I think we and other people have actually used the definitions in all the different targets. And for Sale in particular, I think what appears to happen, but really you want Brian or Alistair to correct me, is that in the different provers you want quite different things, and having a general translation, an ad hoc external general translation, is annoying but super handy at the end of the day. And if you had just locked into Isabel, then half our user base would be sunk.
I just wanted to add, so this was one of the reasons why at this time, like, it was implemented in Haskell and not like before inside Coq, because like you're more flexible in what you can do. And there was actually an interface going to Lean at some point, right, for a bachelor student. So like having the OCaml definitions is in some way like nice because you can bind it like nice and you have the support. But at the same time, like, it also makes it harder to, like, even if these definitions would totally be viable in another proof assistant to write. And it kind of like also like deepens the gap.
I guess also maybe part of the question is what are the sort of things that you want to generate?
Yeah.
Because if most of what you want to generate are maybe definitions, maybe parsing, or maybe sort of tooling, maybe quite a lot of the infrastructure you need to generate that is more or less prover agnostic. But if you start wanting to generate lemmas, for instance, the way you prove something in whole or in Agda or in Lean are different enough that I don't know if there's that much infrastructure that you can kind of share. I don't know.
For the lemma is Lean. That was basically the same thing.
Yeah, because
I
Coq
think
and Lean are basically the same thing.
Exactly, but it gets different if you're talking about notations and all.
Yeah.
Like, then it already gets like fair.
Maybe there is no remote possibility of reaching any kind of conclusion. So we should just stop